Section 11.6 continues with more tests for convergence and divergence, and these are called the ratio and root tests. So in part one, I'm going to go through mainly the conditions for each test, the process, and then in the second part, I'll just do some more examples that will help you with the homework problems. So first, let's take a look at a definition. We'll say a series, summation of all the terms from A sub n, is called absolutely convergent if the series of the absolute value of A sub n is convergent. And we'll jump right into an example here. So let's take a look at the series, an alternating series here. The sum as n goes from 1 to infinity of -1 to the n minus 1 over n squared. So this is alternating. And converges by the alternating series test. Because the limit as n approaches infinity of 1 over n squared is going to equal 0, and the terms are decreasing. But then also, the sum as n goes from 1 to infinity of the absolute value of -1 to the n minus 1 over n squared. So if we're taking the absolute value of this, then every term turns out to be positive. So this is the same as the summation as n goes from 1 to infinity of just 1 over n squared. Which converges because it's a p series where p is greater than 1. So then we would say that the series itself is absolutely convergent. It converges and its absolute value converges. All right, next, let's take a look at the alternating harmonic series. Which is the sum as n goes from 1 to infinity of -1 to the n minus 1 just over n. So this is going to equal 1 minus 1/2 plus 1/3 minus 1/4 and so on is not absolutely convergent. So let's see why. All right, so we saw that in section 11.5, the alternating harmonic series converges. However, The absolute value, though, so if we took the absolute value of this, this is the same as just showing 1 over n. And that this diverges. This is a p series where p is equal to 1. Remember, if p is less than or equal to 1, then that series diverges. So in this case, we don't consider this, or we don't call this to be absolutely convergent. We call this conditionally convergent. So here's the definition. So a series is called conditionally convergent if it is convergent, but it is not absolutely convergent. Let's make a note here. If the series has only positive terms, convergence and absolute convergence are the same thing, because the absolute value of the series is the same thing as the series. Our two examples we were looking at were alternating series. And then this leads to a theorem. If a series is absolutely convergent, then it is convergent. All right, so now we're going to take a look at a ratio test. And a ratio test is good for series with exponents or factorials. And we'll review what factorials are. All right, so here, let's say we're given a series, just the summation of a sub n. And there's going to be 3 parts here. So part 1, if the limit, as n goes to infinity, of the absolute value of a to the n plus 1, or a sub n plus 1, over a sub n is equal to L, and that's less than 1, then the series is absolutely convergent. And then hence convergent. The second part is if the limit, again, of the absolute value of a sub n plus 1 over a sub n is equal to some value that's greater than 1, then a series is divergent. And then the third statement here is if the limit of this ratio, absolute value of this ratio, is equal to 1, then we describe this as being inconclusive. No good. All right, so let's take a look at a few examples. So let's test the series say the sum as n goes from 1 to infinity of negative 1 to the n times n to the fourth over 4 to the n for convergence. So we are going to use the ratio test. So we need to write out what is a sub n plus 1. So that is just the next term. So wherever we see an n, we're going to replace it with an n sub 1. So a sub n plus 1 is going to equal negative 1 to the n plus 1 times n plus 1 to the fourth, and I can just put all of this over 4 to the n plus 1. And then a sub n is just this, what we were given. So it's negative 1 to the n times n to the fourth over 4 to the n. So now I'm going to take the limit as n approaches infinity of the absolute value. And again, instead of dividing these, I could simply multiply by the reciprocal. So we're going to get negative 1 to the n plus 1 times n plus 1 to the fourth over 4 to the n plus 1 times the reciprocal of a sub n. So then we get 4 to the n over negative 1 to the n times n to the fourth. So again, taking the absolute value means I'm going to have just positive ones that are here. So these just sort of divide out because this is always going to be a positive 1 and then a positive 1 here once I take the absolute value. And then I could simplify. I've got one more factor of 4 in our denominator. Or I could write this as 4 to the n times 4, so then 4 to the n's are gone, and I'm just left with the 4. So we could put that out in front. And then what I have left is n plus 1 to the fourth over n to the fourth, so I could write it like this. And then this is always positive anyway, so we get the limit as n approaches infinity of 1/4. And then I could separate this. This will just become 1 plus 1 over n to the fourth, and then 1 over n goes to 0. So I'm just left with 1/4, which is less than 1. So the series is absolutely convergent, hence convergent by the ratio test. So the setting up the test itself is pretty straightforward. It's just all the algebra that's needed can become a little tricky. So that's why I just want to keep practicing these. All right, let's take a look at another example. Let's test the series. The sum as n goes from 1 to infinity of e to the negative n over n factorial for convergence. So let's go back over what factorial means. So if I had 5 factorial, that just means I start with 5 and then times 4 times 3 times 2 times 1. So n factorial is n times n minus 1. So we start with whatever number we're given here or whatever variable, and then we just keep subtracting until we finally get down to times 3 times 2 times 1. So it's n times n minus 1 times n minus 2 all the way down to, provided that n is greater than 3, which is 3 times 2 times 1. So again, we're going to use the ratio test. So what we first need to write out is what is a sub n plus 1. Well, that's going to become e to the opposite, and we need parentheses here, n plus 1, over n plus 1 factorial. And then a sub n is e to the negative n over n factorial. So now the limit, as n goes to infinity, of the absolute value of a sub n plus 1 over a sub n is going to become the limit of the absolute value. Again, I'm going to multiply by the reciprocal. So we're going to have e. Now I'm actually just going to go ahead and distribute this. So e to the negative n minus 1 over n plus 1 factorial times the reciprocal of this. So we get n factorial over e to the negative n. Now I can separate this just like what I did in the last example. I can write this as e to the negative n times e to the negative first, just using laws of exponents. And then I'm going to write this n plus 1 factorial is n plus 1. And then the next part would become n plus 1 and then minus 1. So that's just n, and that would become n factorial. So now we can divide out some common factors. So e to the negative n is gone. N factorial is gone. So I'm just left with and again, this would all be positive, so I no longer need the absolute values. I'm left with e to the negative first, which is a constant, over n plus 1. So that's going to equal 0 as n keeps increasing without bound, which is less than 1. And that again is the first part. So this series converges by the ratio test. All right, next we're going to take a look at the root test. And this one is good for nth powers. So a couple conditions here. If the limit as n goes to infinity of the nth root of this absolute value of a sub n is equal to some value that's less than 1, then the series is absolutely convergent. And just like in the last one, the only thing that's changing here is what we're taking the limit of. So if the limit as n goes to infinity of the nth root of the absolute value of our terms here is equal to some value that's greater than 1, or if it keeps increasing without bound, then the series is divergent. And 3, if the limit as n goes to infinity of the nth root of the absolute value of a sub n is equal to 1, then again, just like in the last test, this would be inconclusive, no good. All right, so let's do an example here. let's test the series. Summation then goes from 1 to infinity of 7n plus 2 over 8n minus 4 to the nth power for convergence. So pretty straightforward. It's just the limit as n goes to infinity of the nth root of the absolute value of a sub n, which becomes the limit as n goes to infinity. So this would be the nth root of 7n plus 2 over 8n minus 4 to the nth power. So the nth root and the nth power cancel out, and we're just left with the limit as n goes to infinity of 7n plus 2 over 8n minus 4. And again, because the degrees are the same here, if I were to divide everything by n, I would just be left with 7/8, which is less than 1. So this series is absolutely convergent by the root test. So we're acquiring a lot of different tests for convergence and divergence. So really the only part from section 11.7 is going to be a list of what to try. So I will definitely write that out at the end of this lesson as well. So let's talk about rearrangements. So we'll say if the series of a sub n is conditionally convergent and R is any real number, there is a rearrangement of this series that has a sum equal to R. And let's take a look at the alternating harmonic series. Which again is this. So remember, we said this is conditionally convergent. So I can rearrange the terms in any order to be any sum I want. So if I want to rearrange it to be any sum I want, I'm rearranging it to converge to be any number I want. So we'll just say we can rearrange it to converge to any number. All right, so in section 11.7, at the very beginning, it lists strategy for testing series. So the simplest one is if we can look to see if the series is of the form 1 over n to the power of p. So we say if the series is of the form the summation of 1 over n to the p, it's a p series. which we know to be convergent if P is greater than 1, and divergent if P is less than or equal to 1. So that is the quickest way to test for convergence or divergence. So if it's not a P series, we'll say if it's of the form, the summation of A times R to the n minus 1, or just A times R to the n, this is a geometric series. And in section 11.2, we looked at a test for divergence and convergence. So we would say convergent if the absolute value of R is less than 1, and divergent if the absolute value of R is greater than or equal to 1. But keep in mind some preliminary algebraic manipulation may be required to bring the series into this form. All right, the third strategy here is if the series is similar to a P series or geometric series, but we can't get it to look exactly like that, then one of the comparison tests should be considered. But something else to note here is the comparison test only applies to series with positive terms. Now, if it happens to have some negative terms, we can apply the comparison test to the sum of the absolute value of A sub n and test for absolute convergence. All right, the fourth strategy is that if you can see that the limit as n goes to infinity of A sub n is not equal to 0, then the test for divergence should be used. All right, if the series is of the form the summation of -1 to the n minus 1 times B sub n, or the summation of -1 to the n times B sub n, then the alternating series test is an obvious possibility. All right, then the next two is what we were just looking at. So if the series involves factorials, or other products including a constant raised to an nth power, we use the ratio test. Now remember, for both the ratio and the root test, if the result turned out to be 1, that was inconclusive. So what that means is we have to go back and see if another test is going to work. So using the root test, that's if A sub n is of the form B sub n to the nth power, so that whole thing would be A sub n, then we use the root test. And then if you also recall, we had an integral test. So if A sub n can be rewritten as f of n, where the integral from 1 to infinity of f of x dx is easily evaluated, then the integral test is effective. But remember, for this, we want to make sure the hypotheses, meaning is our function continuous, positive, and decreasing over that interval. So we'll say assuming the hypotheses of this test are satisfied. All right, so there's a list of strategies because of all these tests. Which one is the best to use other than like once they all get mixed together? This will be a very handy resource to keep looking back at.